Okay, let's try this problem out. We've got an area of 0.45 meters squared in the I-hat direction, has a uniform electric field, 4.2 times 10 to the 5 newtons per coulomb, also in the I-hat direction, moving through it. Draw a sketch, and then how much flux is flowing through the area, and how much charge is separated to cause this quantity of flux. So let's set up with given. We know that the A vector is equal to 0.45 meters squared the I-hat, and that the electric field vector is 4.2 times 10 to the 5 newtons of force for every coulomb of charge on our test charge. And what are we trying to find? Well, for A, we want to draw a sketch of this. For B, we want the amount of flux. And C, we want to know how much charge did it take to create that flux. How much charge had to be separated anyway. So let's solve it. I guess I can do that over here. So let's do A. Now, we'll make I-hat to the right, and so let's just create a certain area, represent it with this, and there's my A vector. Okay, and then I've got some kind of electric field with a certain amount of flux that's going through there. And it's kind of hard to draw it, but you just do the best you can. And so there's my E field. And it's also moving in the I-hat direction. So we've got a certain amount of, you've got this certain electric field. Now, one thing the electric field tells you, or the magnitude of it tells you how much flux you have per unit area. It's kind of a electric flux density. A lot of people refer it to, or call it a density, or how crowded the electric field, or how the field lines are. And that gives you an idea of what E is. But of course, we're just drawing a qualitative drawing here. We don't actually worry too much about how many field lines we actually draw. And then for part B, well, the amount of electric flux is given by, well, I don't need the closed surface here. Let me erase that. E dot dA. And of course, though, here we have a uniform field. The field doesn't depend on the area or anything like that. So really, this just turns into E dot A. So that's pretty simple. And then, so the electric field is 4.2 times 10 to the 5 newtons per coulomb. And then we're going to dot that, well, in the I-hat direction, and then we'll dot that with the area vector, 0.45 meters squared in the I-hat direction. Of course, I dot I is 1. Then we just have to multiply those to get the amount of flux. And so we get a calculator out. 4.2 times 10 to the 5 times 0.45 equals 1.89 times 10. Is that right? Times 10 to the 5. And what are the units here? Well, Newton meters squared per coulomb. And it's one of the odd things in physics to me is that they don't have a name for this collection of units. There's no, that I know of anyway, there's no, they haven't honored any scientist with electric flux. So So that's where you end it right there. Okay, so we have that much flux. Now, how did we create this flux? I mean, what creates electric flux? Well, you have to separate charge. So you have to put positive charge over here somewhere, a certain quantity of positive charge, and you have to have negative charge out here somewhere. Now, we don't really care how these are distributed or where they are. We just want to know how much. And the amount of flux is equal to the amount of charge that's been separated over epsilon naught. Now, we kind of get that from, you can kind of think of this as, we have Gauss's law that we talked about the other day. This is when you surround a charge distribution with some closed surface area, and that's equal to the charge enclosed over epsilon naught. So in a way, we can think of like somewhere over here, I'm going to enclose this separated charge with the Gaussian surface and calculate how much, charge is in there, because I know what quantity of flux. So in a way, I'm using Gauss's law. I'm just skipping this part. I don't really need this. I already used this. Now I just need to solve it for charge. So the charge is just going to be equal to epsilon naught times times the flux. And this is 8.85 times 10 to the negative 12 Newton meters squared under Coulomb squared. I just, the reason I do that like that is because I know that it's the reciprocal of the units for the electric constant. And then I'm going to multiply that by the amount of flux I have, which is 1.89 times 10 to the 5 Newton meters squared per Coulomb. And if I look at units, the newtons cancels the newtons, the meter squared cancels the meter squared, the Coulomb cancels the Coulomb squared, and I'm left with coulombs. Woo. All right, and so the amount of charge that had to be separated is just this value I got times 8.85 times 10 to the negative 12, and I get 1.67 times 10 to the 6 coulombs. And what do we call times 10 to the negative 6 coulombs? Microcoulombs. So you can leave it like this or like this. You guys agree with that? Those of you, this is the first time I've done this problem. So basically, we had to put at least this much positive charge over here, and of course we would have the same amount of negative charge over here in order to get that amount of flux through space. Now, of course, to make a uniform field and all that, we haven't really talked about how to do that, but we will actually when we get to these little devices called capacitors, which is coming soon. Any questions on this? Okay, that is all.